Okay, so one last little thing about independence and conditional independence. In the last lesson, we saw that random variables can be conditionally independent without being independent. So conditional independence does not imply independence. And you might be wondering, does it go the other way? If we know that two random variables are in fact independent, does that mean that they're always going to be conditionally independent? No matter what the conditioning event is? And the answer is no. Okay, conditional independence and independence are just separate things. This is kind of a general thing about conditioning. Conditioning puts us in a parallel universe, and you can't really tell much from a different universe about what's going on in the first one. The way to see that independence doesn't imply conditional independence, well, there's a quick and easy way with coin flips. So let's just do it that way. Let's just think about our boring old sample space. We flip two coins. We can get HH, HT, TH, or TT. And I want to define three events here. Okay, so event A is first is heads. B is second flip is heads. C is both are the same. Okay, so A, just to really belabor this, A is HH, HT. B is HH, TH. And C is HH and TT. Okay. I'm going to assert that A and B are independent. Okay, we've talked about this many times about how the coin flips are independent of each other. The coin doesn't know what happened last time. So yes, A and B are independent. Again, thinking carefully, what that means is that the probability of A is 0.5, the probability of A conditional on B, which, reminding ourselves, is the probability of A and B divided by the probability of B. A and B is just HH, that's 0.25 divided by 0.5, it is 0.5. Same, so yes, the definition of independence is that learning B doesn't tell you anything about A. Okay, but if we're in the world where we know that C has happened, they're not independent anymore. Now, if I know that they're both the same, and I learn that B is heads, okay, well, that tells me, yes, A is also heads. So that by itself is kind of enough to see it. So conditional on C, A and B are not independent. And so again, if we want to do the math to make sure that our intuition is right here, never a bad idea. If we start off with the probability of A conditional on C, which of course is the joint divided by the probability of C. The probability of both A and C, the intersection of A and C, is just HH. Okay. 0.25 divided by 0.5. Okay, so again, I'm getting 0.5, but the probability of A conditional on C and B is now the probability of A and B and C divided by the probability of C B. Okay, and so C, the probability of both being the same and the second one being heads, that is 0.25. Okay, the only outcome that satisfies that is this one. And the probability of A and B and C is also 0.25, and it is 1, which is what our intuition told us. Anyway, so if we know start with the idea that random variables are independent. It doesn't mean they're going to remain independent if we condition on something. And if we start off with random variables that are not independent, we can condition on things that might make them independent. So they really, conditional independence and independence are separate things. You can't judge one from the other. Okay.